and 130 of you not. So we'll keep working on them until I can get all of you up to speed. I'm also going to start, well, next week, the next one's coming up. I added another resistor, but I kept it a little bit simple. So then we'll start twiddling with maybe give you power and a few other different things, and you've got to look at the circuit from a different direction. So we won't do that this week. I'm going to start doing that here soon enough. Okay, you guys need to get units. You need to get units correct, and if you change it to units of K or units of milli, you got to make sure you move it correct. A couple of cases, I think you guys probably got the number about right, but you didn't put the decimal place in, or in anywhere close to where it should be. But in any event, that's not a right answer, right? Okay. All right, so we were just talking about diode bridge rectifiers, as I remember. Seems like we've just kind of gotten through this, right? So we talked about the nature of you guys can't see it. Huh. We've talked about the nature of the Y-wound generator, which is going to have whatever the voltage is across here added to the voltage that's across there, or from here to there, or from there to there. Okay? So at any one point, I suppose I could come up with some color combinations. Say red and blue are the diodes for that one phase. Another phase would be yellow and green. And then the third one would be purple and fuchsia or some other color, right? But ultimately, I sort of do these this way just to show you what's happening in one phase. But in truth, all of those diodes are moving current one direction or another, or resisting current in the other way. So with respect to this coil, right? With respect to this coil, this one's preventing current from going the opposite direction. Instead of, it's forcing it to go that way instead of allowing it to go that way. Same thing true here. This is drawing current this way, but preventing it from coming that way. The same would be true for the other arrangements, such that at any one time, all 6 of those diodes are trying to do something. Okay? We don't really care. I think it's important to sort of have a sense that that's happening, but ultimately, unless we're inside the alternator with a voltmeter measuring each phase, we're never going to know. Most often, what's going to happen is I've got a voltmeter out here, or my oscilloscope, or whatever, so all I'm going to be reading is the very tippy tops where they overlap, like that diagram I showed. So if, in fact, one of the diodes starts failing, then I'm going to lose part of that overlap and I'll see a significant drop coming down. Well, I don't need to look at the phase to go much further. If I see that significant drop coming down, I already know something's wrong. Okay? And if I know something's wrong either at the field, or in the armature itself, or in the diode bridge, what am I going to do? Do not pass go, overhaul the unit, right? Okay, pull unit out, put in box, pull new unit out of box, put back on airplane. The only thing you can say, and the reason you did the test, is now you've got solid evidence that the component you were checking is bad, and in all likelihood, putting the new component in will fix it. Of course, with the caveat that there's a tendency for an old generator to be kind of getting old and the battery starts to go bad and it kills the last remaining life in the generator or the voltage regulator, or so it's not uncommon to suddenly have one go and a week or two later the next one needs to go. That's where we don't do this too well in automotive, but in aviation, having good logbooks, not a bad idea, particularly if you've got 5 or 6 year old battery and the generator goes bad. Okay, talk to the customer. Look, your battery's old too. It died. We're going to rejuvenate it and charge it, but because the generator went bad and it's not working, it's possible the battery isn't going to last you very long. Okay, if they can't afford it, they can't afford it. You put it back in service, but make a note. That way, when they come back 2 months later and say you didn't fix it right, you can say, well, yeah, actually, we had this conversation, right? Question with that.
I was just curious about how is with the way the diodes are designed. What do you do to make it go one way or not? What is the wall river there?
Remember I talked about the 2 different types of doped material, doping?
Okay. Yeah.
So when the electrons try to go one way, they push all the electrons out of the other side, so the part that can easily conduct current gets wider and wider and wider. When the electrons go the other way, they close that depletion zone and they fairly easily jump across. However, to get the depletion zone closed to the point that it cascade conducts requires anywhere from 0.5 volt to 0.7 volts. Okay, it takes a little bit of voltage to turn a diode on. On the other end of the spectrum, going the other direction, it takes a fair amount of voltage to cause a diode to reverse flow. It will do it, and in most cases, unless it's a Zener diode that's designed to do this, when it does flow, it flows with such force that it usually destroys the diode. Okay? The one thing about the diode is your digital multimeter will not be able to turn a diode on. Okay? The resistance reading in a digital multimeter is, the resistance value is really high impedance. They're usually, anywhere from 10 to 100 megohms. Very, very, very high. Very small amount of current being used to measure resistance with a digital multimeter. An analog, that's different, but with a digital multimeter, they don't impact the circuit very much to get their measurement, so it's not enough so the diode will read bad either direction. That's why they have a diode mode. Switch it to diode mode, and that'll give you 0.7 volts, and then one way the diode should read something like 400 or 500 ohms, maybe 600 ohms, somewhere in there. Then the other way, it'll read infinity. It won't, if it's working right. Okay?
What you're saying is the voltmeter doesn't have enough.
A digital voltmeter
Digital.
does it. Yeah, when it measures resistance,
Yeah.
it does it at 0.001 ohm or 0.001
I
volts.
can't read that.
A really, really small amount of voltage. And it's better to do it that way because then you have less impact on. Remember that practice problem you did, like Project 1, 2, or somewhere in there, man, it might have been a little bit later, where you were playing with the analog Simpson meter and you had to calculate out the impact that the meter had on the measurement. Well, the analog meter has a fair amount, has some impact on a measurement, which doesn't mean anything unless you're trying to read, 0.0001 milliamps or a small amount of voltage. Well, that's why the digital meter, and its advantage is it uses very, very small amount of voltage and current. So you don't have to calculate that much out, except it won't turn on a diode. It can't be used to measure a diode or a transistor unless you go to that diode mode. All right. Now the other problem with this arrangement is if I take my little ohm meter or diode meter and start hooking up in here, am I going to be able to measure anything? No, not with all these shorts across the bridge, because these guys are going to read very low resistance. So when I start trying to measure, it'll find another path through. So I got to disconnect things to actually be able to measure the diode bridge. That's why I give you a separate stator and a separate rectifier when you're doing that project. You can't measure it with they're all attached together.
So what makes it a bridge is that they're all acting together, right?
Huh?
What makes it a bridge is that they're all acting together, or
What makes it a bridge is the fact that these your inner and your outer are bridged both this way and this way. Okay, so that in this case the inner is here and the outer is here. For one of the other phases, the inner is here and the outer is here. And for another one, it's here and here.
it's a one-way bridge?
Well, yes, that's true. Okay. So it's true that the rectified generator, because we compress so much in such a small place, is self-limiting. There's a thing called armature reaction, which I do talk about, I think, in another slide. But in the commutator style generator, we had a field here and a field here. And maybe we put one here and we put one here. And as that thing spun around, there would be some dragging of the magnetic fields. But you could drag it quite a bit before they started impinging on each other. This one, where we're getting 12 north-south relationships all at the same time, man, I only have to drag this thing a little bit before the magnetic fields start distorting with the next group, the next pair in line. Okay, so as this thing goes up in speed and load output, armature reaction is going to get worse. So the more load you put on it, the more it distorts and it just doesn't put out any more current. That's it, it's max. So if you put more load on it, what's going to happen is the voltage is just going to start declining. Right? More load, voltage declines even further. The problem is, and it's true, it's self-limiting. That's a fact. You read on the internet, it's self-limiting. Everybody says they're all self-limiting. It's true. If I put a wrench across it, really put some load on it, it will self-limit. And it'll try to do it. And after a while, maybe not instantaneously, but after a while, it'll start getting good and hot. It'll get so hot that it'll start burning the insulation. And you see this kind of blackened area right here? This outer winding got shorted somehow. Okay, pretty black out in here. Okay. It got so hot, the insulation started melting. So we're going to make this thing, we're going to say, I want a 60 amp alternator. And I'm going to make it as light as possible and as small as possible with some cooling fans to be able to produce 60 amps, give or take a little bit. Then I'm going to also design it to where its self-limiting output might be 70 or 80 amps. It's not going to be too much more than 60 amps. And I'm going to give it just enough cooling to be able to handle that 60 amps. But at 70 or 80 or 90 amps, it's probably going to overheat. It'll take it a little bit, but it'll probably overheat. Now, one distinct difference between an automobile alternator and an airplane alternator, when I say it's a 60 amp alternator in the airplane world, I am saying I can run it at 60 amps continuously without it catastrophically failing. So it will not fry it. In an automobile one, I'll give you a good example. Toyota Solara is the one. They claim it's a 100 amp alternator. Well, I've tested it. I've tested one of those up at around 85, and it started getting pretty darn hot. Okay, I brought it down to about 70 amps, and it can handle continuous duty at 70 amps. So I built a modified version of it, put it on one of my airplanes, which only uses like 18 amps. So I got way overkill. But I did test it because I know the ratings that automobile manufacturers give you aren't continuous duty necessarily. They're not going to tell you that. Whereas in the airplane world, the Fed has said there shall be a regulation that mandates and requires any motor and any charging system or anything like that to give you continuous duty values. right? So if you go on the internet, it'll say current limiting, can't put out anymore because of this armature reaction. What they don't realize is that for many units, like an automobile unit, that current limiting place will cause this thing to eventually overheat and do damage to itself. Now, the distinct difference between this and the commentator style one is the commentator style one, you'll have to get a whole lot more armature reaction before it stops producing more current. So when I put a wrench across that one, it can go from cool to way overheated very quickly. Very, very quickly. That one can get so hot that it throws the solder right off of it because it'll heat up really, really quickly if you dead short it.
What's why does it produce heat so much faster?
Well, because remember, this thing only has to distort the magnetic field about that much before it's so distorted that it's not going to produce any more current. Whereas in the commentator style, where I've got 4 field poles that aren't moving and the armature is in the middle, I can distort almost 90 degrees. Okay? That's a significant increase in current. And so in that particular case, let's say I rated at 50 amps, its true self-limiting output might be 170 amps, but its cooling capacity was 55 or 60 amps. Okay? So now you throw a wrench across it, it goes direct to 170 amps, right? Or 180 amp, whatever that is. This one can't do that. It just can't do it. Particularly if it's not at a very high RPM. Okay. So output control is always going to be a function of rotor RPM and field current. You will note that in the world of Continental, they typically connect the Jenny up via a gear drive system, and when they started going to the other from generators to alternators, they had to change the gear ratio a little bit. In the world of Lycoming, they drive them by belts off of the bulkhead that's the starter ring gear. So the end result was they had to create a different pulley, a slightly bigger pulley arrangement for the ring gear because an alternator needs to spin quite a bit faster, a good 20 or 30% faster than a generator to put out the same equivalent. Well, it's not so much to put out the same equivalent, it's that a generator will produce current at very slow RPM all the way up through fast. An alternator, it won't start producing enough current. It won't start producing enough current to get the diodes to work until it exceeds a certain RPM. And when you guys do the test drive on your alternators, you'll see there's a coming in speed. You're bringing the RPM somewhere around 1,000, 1,200, somewhere in there. You won't see anything on the oscilloscope, and all of a sudden, boom, it'll start appearing. That's the generator coming online. Well, if the alternator doesn't come online until 1,000, 1,200 RPM, I'm going to need to be going at least 2, if not 3 times, 4 times faster than the engine, because there are a lot of engines that idle fairly slow RPM. So I'm going to need to get that thing spun up just a little bit, just at idle, or it won't even charge at idle. Okay, so I might have different parts to connect this alternator to the engine than I would have with a commutator style generator. I need to control the way this thing behaves by trying to keep voltage about the same. The reason for that is most components don't like wild changes in voltage. Okay, a light bulb is designed to operate at a fairly narrow band of voltage. If I start running it too high or too low, it's going to behave badly, and its service life is going to be cut significantly. Motors, same thing. They're designed to have X amount of current and voltage going through them. If I run them outside of those parameters, their service life is going to decline significantly. So anytime there's an unintended voltage drop or voltage not at what you want, its life is going to decline greatly. Same with batteries, it's even more critical. I really want to make sure I don't take a battery too far, particularly at high voltage, or I'll damage it badly. So we want to control the voltage, but we've got to control it in a fairly responsive way, because what's usually going to happen, particularly with a lead acid battery, they've got a fair amount of resistance. So if I suddenly turn another current user on, that's going to create a demand. Given the resistance to the battery, it's going to try and drop voltage down, right? So the alternator's voltage control, or the generator's voltage control, has to respond pretty quickly to get that voltage back up, to make up for, so that your voltage transients aren't that significant. It's also quite a bit easier to control for voltage than it is for current. Currents, it's not too bad controlling for current, just sort of an upper limit or other behavior, but trying to regulate specific current, the specific amount of current is quite a bit more complex. So, and then if we go into the world of AC, it's also really important to keep the frequency fixed. So maybe today or next week, when you dive into inductive reactance, inductive and capacitive reactance, you will see that frequency, both values or both formulas include a function of frequency. And that really, really hurts our circuit. I did check it just today, but right now, because of inductive and capacitive reactance imbalance in the building, we were operating at about 0.89 efficiency, or 89% of the power that the power company is selling us is being used. The other 11% isn't getting to us. We're paying for it, but it isn't getting to us because of this reactance. So if I change the frequency, everything I designed to try and control that reactance is going to go out the window. So instead of being 11% off, I might be 25% off just by changing the frequency, 5 or 10 cycles per second. Okay, so where AC matters, we have to keep rotor RPM, and it doesn't matter whether it's a field spinning or armature spinning. We got to keep rotor RPM very, very constant. If we go out and hit the button right there and see what the actual frequency is, you'll see it's 59.998 or 60.002 or 0.02. Pretty tightly controlled, right in around 60 cycles per second. Now that doesn't necessarily mean that's actual rotor RPM, because remember we were talking in here, I'm going to get 6 cycles per revolution. Now the big power stations where I've got an armature field that's this big around, I can have fit way more than 6, right? Okay. Fortunately, in most vehicles that go places like airplanes, cars, boats, trains, etc., we have a battery to get the darn thing started and to act as a backup and redundant system. And because the battery likes DC, we just designed the whole thing to be a DC system. Then rotor RPM doesn't matter, which is fortunate because we can't really control rotor RPM. Until we make this real fancy whiz-bang go-fast F-18 or Boeing whatever, and we design it to run on AC, or parts of it to run on AC. Now I got the problem of an engine that needs to vary and a generator that can't vary. So I'm going to have to put a very specialized transmission between the two, called a constant speed drive, or CSD, so that no matter what gets put in, RPM-wise, or load, the output's 400 cycles, or puts out 400 cycle AC. Okay, that's a very expensive proposition. Those CSDs are not cheap. I remember one of my students brought one in, probably wasn't supposed to take it off base, but brought one in, and it's sort of this big huge thing, F-18 constant CSD, and we did a little bit of work trying to figure out how much it cost, and it was like it cost as much as everybody in the class made in a year, you know. It was just huge, hugely expensive. Okay. If I can design this thing around being able to vary the amount of current going to the field, I can vary that current based upon the output voltage. So I got to have a potentiometer, right? I got to have a potentiometer, and then I'm going to real quick measure the output voltage, change it, 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 smack the pilot because he keeps changing the RPM, measure the output voltage, change it. That's a lot of workload, right? So I'm going to want to automate this some. Very, very quickly. I'm going to, oh man, I'm doing. I got to do that for each engine. Plus, I got an APU in the back. I got to do it for it too. Man, it's a whole lot of hopping around, grabbing my voltmeter, turning the knob. So there's a couple of ways of doing it. The little bitty ones are in the interest of reducing the amount of power being used, because we're going to have to invest a little bit of current into the field, right? So I'm going to have to pay maybe 1.5 amps or 2 amps of field current to get 60 amps out the armature side, right? Well, I could design the circuit to where plus comes up like this to my field down here to ground and have a big variable resistor, right? And as I bring the resistance up or down, I'm going to change the total circuit resistance and the amount of current going through. However, this guy here is going to get fairly hot and consume a fair amount of current. So no matter what, I'm still going to be using 3 or 4 amps of current, maybe 2 amps here and 2 amps here, something like that. As opposed to positive to there, that goes to ground, and then I just put a little switch in here. Okay? And if I take the switch, close the switch, what happens to the field? Current starts flowing, magnetic field starts building up. If I open the switch, magnetic field starts collapsing. Close the switch, starts building up. Open the switch, starts collapsing. It's not instantaneous. So if I sit there and open and close the switch real fast, the magnetic field is going to be doing this. Okay? More open time, the magnetic field is going to get small. More close time or on time, the magnetic field is going to get big. During those periods where the switch is open, no current's flowing. So I've got nothing getting hot as a result of providing that resistance. Now, what happens when I take a big magnetic field going pulse, 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 pulse to the voltage system of the main bus?
A lot of noise.
It starts going pulse, 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 pulse. And you can feel it in the airplane. Well, you can't, but all your audio is going to feel it, going to hear it. You can actually hear AC. If you get real quiet, you can hear the transformers in these lights buzz a little bit. Okay? Because it's doing that pulsing. So the downside of using a switching type field regulator is they do make some noise. Okay, well, so now we're going to have to design some more stuff in the circuit to try and suppress that noise a little bit. But we can do that. We can work on it. If I use a mechanical switch, we can do that, but what's going to happen when the switch opens and the magnetic field is trying to collapse? Is it going to arc a little bit? And when it closes, it's going to arc a little bit as it's coming close. and arc and arc and arc and arc. So
Arc is jumping, right?
arc is jumping, but arc is hot and eroding a little bit of the, creating a little pits and a little bit of erosion on those points, along with mechanical erosion from running into each other all the time. So those points have a finite lifespan if in fact I have to use a mechanical switch. Now, when we come back later on and look at a 3-unit regulator, you'll see we put a couple of other resistors in there to try and help absorb some of that spark, but it's not 100%. So if I could come up with an electric switch instead of a physical mechanical switch, I could eliminate that arcing. Well, it turns out if I take a couple of them diodes we were talking about and hook them up in a certain way, they become an electronically controlled switch, otherwise known as a transistor, where I can use a very small amount of current to turn a circuit on or turn it off. On, off, on, off, on, off, no contacts. All I'm doing is saying, be conductive, don't be conductive. Be conductive, don't be conductive. Okay? While it's conductive, that part might get a little bit warm, but if we give a good heat sink, it'll work. Okay. So, the other thing that's important to notice, I drew this. There's a positive and a ground here. The switch, in this case, the controlling device, is on the negative side of the load, isn't it? Of the field. So it's negatively controlled. I could easily put the switch there, and it's positively controlled. The load doesn't care. The battery doesn't care. Ground doesn't care. Okay? I can put it on either side. And that matters particularly when we get into carbon pile regulators, because with a carbon pile regulator, part of how you hook it up has to maintain the correct polarity. The part that goes to the field doesn't, but the part that senses voltage does have to maintain polarity. So when I can't take my carbon pile regulator and just flip it around into here. It's got to maintain the exact same orientation, or it'll read backwards. As the voltage goes up, it'll try to cause the voltage to go even higher. Okay. So we've got all kinds of fancy stuff. We've got mechanical, big mechanical switching regulator, 3-unit Hosgod's thing. For an alternator, we've still got a mechanical switch controlling it. Or we could get a nice big transistor and use it in an analog manner to where this thing just acts like a variable resistor, going up and down gradually. Gets kind of hot though, so we have to give it a big heat sink. Or we can go even smaller and just use this little bitty transistor here, bonded to this little heat sink here, and this guy just turns on and off, so it doesn't generate nearly the same amount of heat. Okay, so generations changed. We went from big heavy thing down to little bitty thing like this, and they've actually made this so small that we can bundle it all up and put it in the brush assembly that goes into the back of the alternator. So the brush assembly regulator, everything but the diode pack is all one unit. Many of your automotive type alternators, that's what they do.
So whether it's a positive or negative control system, it depends on which side of the load the switching mechanism's on?
Correct.
Okay.
The positive versus negative and the relationship between the load and the control. And this isn't universal. In today's world, we typically control human interface type switching, the on-off switch, etc., on the positive side to make the positive lead as short as possible for safety reasons. And we control computer controls The computer might control the very same circuit on the negative side. And that's because of the way the type of transistor that's doing it is an NPN, and they only work on the negative side of the load. But they respond much better as a high power device. So for example, you get in your car, turn the key. The key comes on and it sends power out to the computer. It also sends power out to the fuel pump relay. Power goes to the fuel pump relay, only the relay doesn't come on because it goes from the fuel pump relay over to the computer. And the computer says, I'm not turning the fuel pump on, the engine isn't running. That's not safe to have the fuel pump on when the engine is not running. So the computer's going to sit there and say, I'm not doing anything, until it says, oh, I got some information from the engine, a crank reference sensor. Tells me the engine's actually spinning. Okay, now I'm going to ground the fuel pump relay. It got power, I know it's got power, now I'm going to ground it. So I'm going to turn it on the negative side. It's going to click and then send power over to the fuel pump. The fuel pump's going to come on. However, it's going to take a while cranking for the fuel pump pressure to come up to cause the engine to run. So we're going to go back to the drawing board and say, when you first turn the key on, the computer's going to go, oh, the key just came on, I got power, I'm going to turn the fuel pump relay on and then turn it off until I see crank reference. So it's going to run the fuel pump just long enough to bring the pressure up. And you can hear it. If you're in there quietly, it's usually in the tank, so it's a little hard to hear. But you turn it on, it'll run for a little bit. Then when you start cranking, it'll come back on and start running again. Okay? The computer has activated the fuel pump by turning a relay on from the negative side. The switch is over here. That's the coil of the relay. There's another power out to the relay, out to the fuel pump. So the fuel pump itself is controlled on the positive side of the relay, but the relay is controlled on the negative side by the computer because the computer uses NPN transistors, which have to be negative of the load. Now, I won't get too deep into that yet. So as a general rule, computers control on the negative side, humans control on the positive side. But like I say, in the world of voltage regulators, we did both. There's plenty of both. So in this case, I've got my bridge rectifier. I've got my Y wound. I've now got a voltage regulator, which I took power to the voltage regulator out to the field of ground. What isn't shown here is there actually should be a little ground here as well. Because this thing needs to get some voltage to do its magic. It also needs to be able to measure between power and ground to know what the voltage is, right? To be able to say, make this high or low. There are some regulator circuit designs that they actually have a separate lead. They actually, and I don't know if I showed this to you guys or not, it's coming later, where they actually have a separate little bridge rectifier comes off of here to feed that information to the voltage regulator to give it the most accurate voltage reading possible. Oh, it's the next slide, Judd. There it is. So what we're going to do here, you guys recognize stuff. Here's your armature, your stator, not moving around. There's your bridge rectifier, putting out all its good stuff. I've got a little capacitor filter to ground. That's the negative side. Electricity is going to come up that way to the battery on the positive side. In truth, it's going the other way, but for now we'll take it as going that way. Our field rotor's here. And our field rotor is going to get, when I turn the key on, it's going to get electricity out to this node, out here, up to there, to the field rotor, back down to here, back down into here, and then somehow this transistor needs to connect it to ground. So that transistor is going to control the field on the negative side. When that thing opens and lets current flow, it's going to connect the rotor to ground, causing it to excite. I'm also going to bring another branch off of each one of these with the diode trio over to this node here. That then allows this part of the control part of the regulator to very closely know what the voltage is. Now this guy's kind of cool. I'm going to do a couple things. One thing I'm going to do is I'm going to send power all the way out to here for the control side, to let the control side know what to do. I'm going to have a little indicator lamp, and the little indicator lamp's going to come out to here and out to this node. If in fact something goes wrong out here and this side's still working, this will become negative. That will be positive, the light will come on. Otherwise, during most normal operation, that will be positive, that stays positive, no voltage potential, the light stays out. Now, in today's time, that's now your malfunction indicator. So that's really just a signal to the computer. I'm also going to have a little bit of a voltage drop coming off of the battery here, just to suppress, actually to suppress a little bit of problem from the indicator lamp. So now, the way I'm going to sense things is, and this is a little strange, this guy is an NPN transistor. What that means is, if I make this positive, it'll turn on. So if I cause this to be positive right here, it will turn on. If I cause it to be negative, it will turn off. So the way to get it to turn positive is to let some positive come in from here, right? So if I shut this transistor off, this resistor is going to let this side become positive. There'll be a little bit of a voltage drop across that diode. We got to put that diode in here and that resistor in there, because when this thing's starting to go up or down, the pulse coming from the magnetic field needs a place to go. So this will allow that pulse to do a loop here and not hurt anything. So on this side, if I take and turn this transistor on, it's going to connect it to ground, causing all of this to go in. When I turn this transistor off, it no longer has a path to ground, so this side is going to become high, causing that transistor to turn on. Well, the way I'm going to control this transistor here is with the Zener diode. So a Zener diode, let's say I cause it to be 5.6 volts. So anything above 5.6 volts, this guy starts to go high. Okay, and starts sending electrons across here. Between here and here, I've got, say, 13 volts. But I've got a voltage divider. So I'm going to drop about 5 volts here and roughly 8 volts here, somewhere in there, so that, and then I can adjust it a little bit with this variable resistor here, so that my set point here equals desired system voltage up here, right? So then what's going to happen is when this guy gets high, the voltage goes up, it gets high, it starts conducting, this goes to ground, this goes to ground, this goes to ground, and it shuts off the path to the field. The field starts to collapse. Okay, well the voltage was high, we want the field to start collapsing. So now it starts going low. This starts going low, it stops conducting here. This guy shuts off, no longer provides a path to here. So now battery voltage can come this way, across that resistor, into here, across this resistor, causing this to go high, causing this to turn on, turning the field back on. I'm never going to test you on that. But this guy is, that guy's going to function in that, that's not a switching, it's an analog one. So that's going to be this really, really big fat transistor here. Okay, it's doing, schematically it looks the same, doesn't it? But this is going to be the big heavy one that's got to do a heat sink, because it's going to act in an analog manner, varying up and down. It's probably going to be controlled by this little bitty transistor here, which is going to be your TR2 over here. It's a little hard to see, but my guess is this guy right here is the Zener diode that's giving you your voltage reference. Somewhere, some of these guys are your voltage divider circuit. That right there is your variable resistor for adjusting the set point. That's this guy right here. Okay, so that schematic is basically this unit right here.
Your voltage reference is ultimately coming from the diode trio because it's going up.
Well, the voltage reference for the primary transistor is, okay, for the control part of the circuit, it's actually measuring at the top of the battery, okay, across the voltage divider. This one, as you adjust to whatever you want it to be, okay, this then becomes your set point at 13, let's say we want 13.68 volts. Across here, I knew I was going to get, let's say I've got 5.6 volts here, and I'm going to adjust this to be 13.68 or 13.6, 5.6, so what I got, 8 volts. So I'm going to adjust this to be an 8 volt drop to here. So now my set point on this is going to be, it's going to come on or go off right around that 5.6 volts. It goes below, it goes one way, it goes above, it goes the other way. This diode, being a Zener diode, it conducts current backwards in reverse bias. So it's a check valve, lets current go one way, prevents current going the other way until it gets above 5.6 volts. Then it lets it go. Once it lets it go, it then starts letting this conduct. When this conducts, it then causes this guy to conduct. Actually, it causes this guy to go negative because it connects it, so it shuts this one off. Okay. So what we're doing is we're going to switch back and forth. The two transistors switch behavior. That part's a little hard to see, but we need that because voltage goes high, that conducts. That needs to shut the field off. So I put a second transistor in there to reverse the behavior. If I do that as a logic circuit, it would look like a little inverter reversing the signal. Okay, but that is standard, pretty common regulator type digital regulator. This one's analog. It is not the switching type. Heavier, wastes a lot more heat. And if you play with electronics enough, you'll get to the point where you'll just look at that circuit and go, oh yeah, it goes burn it and does that. And okay. The switching kind, that little bitty one, what it's going to do is it's going to go, I'm going to turn the field on, boom, boom, at the same time. And like a metronome, just click on, click on, click on. Maybe I'll turn it on 500 times a second or 100 times a second. 100 times a second, I'm going to turn it on. However, I'm going to turn it off at some time before the next 100th of a second. And that duty cycle of being on versus off is what's going to cause the magnetic field to pulse up here or all the way down here. Okay, so here I'm at about 50% on time. There I'm probably about 20%, 10%, back up to 50%, up to 80%. Now my magnetic field is way out here. It's gotten a whole lot bigger. 80, 90%, back to 50, back down to 10, up to 20. Okay, but each time, on, off, on, off, on, off. So they usually will have, and this is a little bit more difficult to see, but oftentimes they'll either set up a capacitive oscillator or they'll actually have a dedicated chip that then controls the transistor and says turn on, turn on, turn on, and then based on voltage, it regulates it up or down, or the amount of on time within each cycle. Okay, so this uses way less current to run the control part. it's still got to provide, you know, an amp to 2 to 3 amps out to the field, or if it's a very big unit, maybe a little bit more. But that's only the output switching transistor that needs to be that heavy. The rest of it can be a little bitty light duty circuit. So it got very convenient for no reason other than manufacturers, not only do they design stuff around what makes it easiest to build it, but also they design it around product satisfaction. So if I design something like my alternator, and I sell it to all the people in all the land in all of their cars, if it is so convoluted and confusing that none of the mechanics can figure it out, ultimately the customer's not going to be happy, are they? So fairly early on they said, well, most mechanics aren't going to figure out all the solid state stuff. So we're going to design it around pull the unit out, throw it away, put a new unit in. If it's not putting out, pull it out, either get it overhauled, throw it away, whatever you do. But you don't do any work inside it. And you don't really need to know whether or not it works. All you need to know is fire everything up. Do you have more than battery voltage? If you don't have more than battery voltage, clearly the Jenny isn't Jenning. If you have more than battery voltage, it probably is Jenning. Now, we could do some things if I had a separate voltage regulator to bypass the voltage regulator and verify that the Jenny is working and the voltage regulator is bad, or by process of elimination, the reverse. But at the end of the day, you're still probably going to want to replace both anyways. And the manufacturer just said, why don't we just build it all as one unit? Since we can do that, we'll build it all as one unit. And then not only have we simplified the job of the mechanic, but our product reliability, at least from the customer's perspective, is going to be, I had something break and they fixed it, I'm happy, on we go. As opposed to, I had something break and nobody can figure out how to fix it. Right? Now you'll note in that prior diagram we have the little idiot light and there was a separate little resistor going around there. Let's go back to that if I can get it to stop. When I first turn this thing on, okay, I'm going to have battery power go this way, down to here, and oops, it can't go that way. Diode say no, can't go that way. All right, that's okay. We'll send battery power out this way. Okay, well, we can go out to here, but we have to go through the lamp or the resistor or something to get to here to excite this stuff up to get this guy excited so it actually starts producing power. Well, early on, when they first started designing these systems, they didn't put that resistor in there. So everything was fat, hunky-dory until the light bulb burned out. Then you fire it up, no indicator lamp, right? Everything's great. Only nothing works because you've got no way to originally excite the field in the first place. So that's why they put the other little resistor in the path there. The other thing was they didn't realize that people weren't all that well trained about the indicator lamp. How many of you check the indicator lamp every time you start your car? Your malfunction indicator lamp is actually supposed to do some things. Key on, it's supposed to do a couple of things. Do you guys know what it's supposed to do? Have you read the maintenance manual to know what it's supposed to do? It is supposed to do some things. It's not entirely consistent, but for the most part, yeah, it should do. Same thing here. Key on, it should do something, come on, and then once you get the thing started, boom, it then goes out. Right? Yeah, they didn't realize that the public actually never looked at those stupid lights. So they pretty quickly figured out they had to redesign some things. I changed a lot of those light bulbs. All right, so this one shows essentially the same circuit. I just put a little dummy light bulb in there. Now, another way of doing this is instead of this being here, is I could run a line from here over to my computer. And it says, Jenny isn't working, and the computer says, malfunction indicator light on. Because it actually controls it now, so. So typically, in this particular unit, you've got the field spinning. So it's not a lot of weight. The bearings are never loaded that much. You've got brushes in there that they're on a slip ring. They're going to last a pretty long time. So there's not much to go wrong with it. Well, commonly what fails on these, occasionally it is the brushes. They're in there long enough for the brushes to wear out. More often though, either the rectifier plate, just from heat and vibration, breaks itself and diodes start breaking, or the regulator fails in one form or another. So you can bypass the regulator. We've said the switch is a regulator. I am the human wire. I just bypassed it. When I bypass it, what should happen? Full magnetism. Full magnetism, output should go skyrocketing. If I got the RPM up, it's a 12-volt system, I should see 18, 19, 20, 22 volts. Way up there. Don't want to do that long, but that tells me that if I bypass the regulator and suddenly everything's working, then it was the regulator that was bad. Called full fielding the unit. It's not the same as flashing the field. Flashing the field is very different. That's only for commutator style. This we can do it on anything. Full field it, and it tells us whether or not it was the generator or the voltage regulator. However, in all likelihood, you're going to be replacing both. Now, there could be an exception. The generator, because of bearing noise or whatever, went bad, and a year later, you didn't put a new regulator in, but a year later, the regulator now gives up the ghost. Well, the generator is still virtually brand new. You decide you do a little bit of diagnosis, full field the generator. Hey man, it's putting out all kinds. Clearly the regulator isn't working. Put a new regulator in, everybody's happy. So there can be some cases. However, if the manufacturer has taken the voltage regulator and made it really little bitty thing and buried it inside the brush housing, or inside a little, something inside the alternator, it's going to be very difficult for you to figure out, is this negative controlled? Is it positive controlled? Do I bypass it by going to positive? I don't even have a place to connect to it, other than maybe tapping into the brushes or something. Well, then at that case, if it's internal anyways, the only way you're going to be able to fix it is to replace the unit as a whole in general anyway. You can buy parts for alternators too, but in most cases you're not going to do that. In the world of aviation, because we started with generators, most of the time voltage regulators are separate from the generator or the alternator. And so it's fairly common to see one replaced and not the other. The other side of that is the alternator is $500 and the regulator is $400 or $300. So it behooves you to just do one, right? Okay, as opposed to $38 from Kragen for both. All right, okay. So again, a 12-volt system ought to go up, double it for a 24-volt system. You want to be a little bit careful, because when you go to full field it and bring your RPM up, you're going to see, 40, 45 volts, something like that on a 24-volt system. So all you're trying to do is just see the voltage go up above battery. So there's an example of full fielding it. I am the human wire and I just bypass. Right? So if it's on the negative side, and now I've got a regulator. I gave it some power so it knows what the voltage is. That power is also going to go to the field. The field's then going to come back, and somehow the regulator is going to control it on the negative side. So I've got to bypass this to ground to get it to go full field. Right? Now, this is not flashing the field. flashing the field in commutator style generators, you're hooking the wire up the exact same way, but the reason is entirely different. Okay? And there are FAA test questions about both, so make sure you know. Full fielding is a diagnostic testing. Flashing the field is something you do when you first install commutator style generator to establish residual magnetism. Okay, so voltage regulation in the older units, and I think I showed a diagram of this, so I'll walk through it a little bit later. But we had to make sure that we regulated the voltage, and we could do it with a switch. We didn't have them diodes and all that cool fancy stuff. So we had to make a very convoluted little springy switch thingy kind of points and doing all, it's kind of hard to make, right? Then to make something like that, because it's a commutator style generator and it doesn't self-limit in current like an alternator does, we were talking about earlier. If in fact something gets a dead short, it'll try to put out a whole bunch of amperage to the degree that it'll catastrophically fail some things, including the generator, possibly parts of the electrical system. So we're going to put something in here that senses current. And if the current gets too high, we're going to take the generator offline. So to do that, that means the output armature from the generator has to go through this unit and to the battery, and it disconnects it. The other thing is a commutator style generator is also known as an electric motor. There's a few subtle differences, but it will motor. If I start bringing the voltage input to it higher than the output, it, instead of pushing electrons, it'll take electrons in and start trying to make the engine go faster. So if the current starts going backwards, I got to disconnect it also. In that instance where it starts going backwards. So I don't need to do that in an alternator, do I? Because current can't go backwards because the diodes say no. Not there. About the only thing, current limiting not necessary, reverse current not necessary. The one thing that an alternator can do though, is it can full field. So it can go too high a voltage. So there are a number of airplane installations with alternators that actually have over voltage protection. It's rare to see that in an automobile. They just don't do it. But there are instances in airplanes where you'll see an over voltage device, might even have a little idiot light, might have a separate circuit breaker that pops if the voltage goes higher. What they do, it's actually kind of stupid. It's a little suicidal, I guess is the way to think. They do what's called a crowbar safety device. It's like taking a crowbar and hitting yourself in the head with it. I don't know why they use the term crowbar, but essentially what happens is part of the voltage regulator circuit says if the voltage goes too high, I'm going to take the input lead coming from the circuit breaker and attach it to ground. That's going to dead short the circuit breaker, causing the circuit breaker to pop, which is going to shut everything down because the voltage went too high. Well, what if the circuit breaker doesn't pop? I mean, okay, you're relying on the circuit breaker to actually be functional. So, and those exist in airplanes. I'm just dumbfounded that the FAA ever signed off on that. All right, so yeah, this shows a voltage regulator. In this case, we're now commutator style. The armature is the rotor. The field is stationary. I can put the regulator measuring voltage here. It also needs its own ground. And control the field on the positive side. Or I can control the field on the negative side. Either way. So, again, we use the 3-unit regulator. Kind of said that, so I'm gonna move on. The problem was, once we got to the bigger units, those points, there was just too much field current. So opening and closing those points would cause them to fry. So I had to build an analog device, a big variable resistor that I could analog control up or down, no switching at all. But because it's a big resistor that I'm dumping 4, 5, 8, 10 amps through, it's going to get hot. So I had to put a bunch of cooling fins on there. And then I'm going to control that resistor by running voltage across a voltage coil and applying a little bit of magnetism. And the magnetism is going to pull against the spring. So the spring is going to go one direction, the magnetism is going to go the other direction. Okay? Well, the magnetism is only going to go the direction that the current goes through the wire that wraps around the armature of the magnet, right? If the current goes the opposite direction, it's going to work the wrong direction. It's going to push in the direction of the spring rather than push against the spring. So I've got to make sure the current goes through that sensing magnet in the correct direction. So what we did is we created a bunch of carbon discs that, you know, sort of concave surface like this, slightly concave, and I'm over exaggerating it. If I start to mash this, these guys are going to flatten out and there'll be more and more contact area. So the resistance will go down. So if I take a big spring and mash against this, its resistance is going to go down and it'll start allowing more current. So I'm going to allow current to come through this thing and out to the field. And as it mashes this thing, more current can come through the field, causing voltage to go up. As the voltage goes up, there's a little voltage sensing coil in here pulling against the spring, unmashing the carbon pile. So voltage goes up, the voltage sensing coil tries to unmash the carbon pile, increasing resistance, dropping field magnetism, causing the voltage to come back down, the output voltage to come back down, right? Hence the carbon pile. Clever name, huh? So, and that's kind of what that says. Then, of course, we had to add another couple of things in the circuit. One was we needed a way to adjust this thing a little bit in the field. Okay, well, it turns out just about every voltage regulator out there, there's a way to adjust it. It's not necessarily meant to be field adjustable. But these guys had to be field adjustable because they were installed on bigger units that typically had multiple engines with multiple generators. And we needed to make sure each generator is operating at about the same output. Otherwise, we're going to get one generator motoring the other generator. So we're going to have to be careful to kind of prevent that. We're also going to have to put in some kind of an equalizing circuit that automatically adjusts depending on whether or not I've got some changes in RPM. Because we cannot have that situation where one generator is motoring another generator. It'll overheat that, it'll fry them both very, very quickly. So then this balancing circuit, and I show a couple of pictures here in a little bit. Actually, the next slide, we'll walk through those. Okay, this keeps everybody balanced. So let's look at the voltage regulator first. We got a carbon stack, and we got this big diaphragm spring. It's called a Belleville spring, a Belleville washer. It flexes this way. Very much like a clutch plate, if you've ever seen a clutch plate. It wants to spring up. So it's pushing up against the plunger, compressing all this. I'm going to take my output to the field, it's on the negative side. I'm gonna bring it in here. I'm gonna run around here like this. I'm gonna run it through the carbon pile, and then I'm gonna run it to here, and this is insulated, out this wire over to terminal B. Okay, and then I can connect that to ground. So power goes to the field goes to A goes to there to B goes to ground. At the same time, I'm going to have a little bit of that power come through this circuit, right down through here into this voltage sensing coil. Zippity-doo-dah, zippity-doo-dah. Then it's going to come back out here along that line to B. That voltage sensing coil has to follow the coil rule, the left-hand coil rule. Okay, so in terms of polarity, it's got to keep the North Pole. And if I send the current the other way, now the magnetism is going to work the opposite direction, and it's going to, instead of pulling back when the voltage goes up, it's going to push the spring, which is going to cause the voltage to go even higher. Okay? What I want is the voltage goes high, this pulls the carbon pile back, resistance goes up, current to the field goes down. Okay? So I can't switch that voltage sensing coil. I'm also going to have, note I said I'm going to have an ability to adjust this. I'm also going to have another circuit in here that I can use for sensing voltage balance. I don't have to hook that up. If I just got a single engine, I leave it unhooked. Or I can bring that into part of the circuit in an equalizing circuit, and I'm going to use that to sense balance, and then I'm going to also take from D all the way around through K, I'm going to use this little coil right here to send current one way to add to the push of the spring, or the opposite direction to pull on the spring. And then I'm going to wire these things in mirrored manner so that while one generator, the equalizing coil, is turning it higher, the other generator, the equalizing coil, is backing it off. So the two generators behave opposite, or the two regulators behave opposite of each other. However, to do that, I'm going to have to introduce a very small voltage drop in the output of the generator. So I can either do it on the positive side of the armature or the negative side, but I got to create a little bit of a voltage drop. So this is the same diagram, only now I've got a generator in here. I've got a field in here. The generator is a rotating armature. The field grounds, so this getting positive from the carbon pile. The carbon pile attaches like this. I've got positive coming down here, going through the carbon pile out to the field to ground. I've also got my voltage sensing coil here, variable adjuster right there. Okay, I got that all nice and hooked up. I got the exact same thing mirrored over here. Okay, the output from the generator is going to come up to the main bus, only I'm going to get a very, very high wattage resistor. Okay, it can handle hundreds of watts, but it's very little resistance, 0.0025. That's not a lot of resistance, is it? And given that it's that finite amount, it's also got to be pretty darn accurate. So these things aren't going to be cheap. They're a little expensive to make. But when one Gen-Jenny isn't putting out as much as the other Gen-Jenny, this one's not putting out as much. So what's going to happen is this guy at 200 amps is going to create a half a volt drop here. This guy at 100 amp is going to only create a quarter volt drop. So that means that while this is 28 volts, this is actually 27 3/4, and that might be 28 1/4. So there's a little bit of a voltage difference between the two. that's enough to cause some current to flow through the second equalizing coil, across down to here, through that equalizing coil, the opposite direction, and back this way. That's going to cause, in one case, this carbon pile to back off a little bit, lowering the output and the amperage. And this one, it's going to cause the carbon pile to compress, bringing the power output of this unit up some. So it's going to try and get them both to come back to 150. Guys with me on that? Now, given that we've only got 0.0025 ohms, man, howdy, a little bit of an electrical connection, anything, anywhere. Okay, the slightest amount of corrosion, the slightest amount of anything. It doesn't take much corrosion to get to 0.0025 ohms, does it? Right? In fact, my wire lengths are different. I mean, a number of things can cause problems with it. So it's a sensitive system. It's doable. It did work. A second version of this is going to be the same thing. We're going to add a few things. So, for example, we put a shunt in here and a shunt in there. They also have a little bit of a voltage drop across them, but we needed some amp gauges. So we put that there. Because we put the shunts there, we said, well, let's put our voltage drop shunts on the negative side instead. So, same thing, we've got the field grounds through here, only now ground through the shunt. The regulator supplies positive to the field, and we've got all that part the same. The only difference is we're going to take and measure the voltage potential between E and E. And as soon as this is 0.25, that's 0.5, so I'm now going to get some voltage going one way through this coil, across here, the opposite direction through that coil, and back up to there, causing, again, this field to get stronger, that carbon pile to compress, that carbon pile to decompress, and that field to get weaker. The only difference is we put those shunts on the negative side. Probably because we had the amp meter shunts up there. Okay? Again, not too terrible of a diagram. Also looks like we've got a master relay in here. A couple of master relays for each side. All right, that's a good place to stop for dinner.